Hello students. So today we are going to talk about another concept, that is confounding. I do understand that most of you have done this topic in your undergraduate, and I do understand that you are comfortable in solving different types of problem. For example, if I ask you that these are the effects which are going to be confounded, then how the blocks are going to be constructed and so on, those things you understand better than anybody else. But my issue is here that you know the mechanical part. Given any two effects, you can always found the interaction effects, you can always found the blocks. But my question is this: what is the theory behind this? What are the fundamentals behind that theory which are working and because of which you try to take those types of actions? So in this lecture I am going to demonstrate, number one, what is confounding, and number two, that in case if I try to assign any treatment combination in any blocks, then what does this makes happen? What happens after that? Right. So first question I try to understand is what is confounding. So you may recall that when we had started the concept of incomplete block design, at that time we had discussed that one of the basic problem in designs of experiment is that when the number of factors affecting the experiment become large, then you need a larger amount of experimental material. And one of the basic objective that we tried to achieve was that how to choose the important factors, or how to assign the factors in different blocks such that the outcome can be obtained with maximum efficiency and whatever is your objective, that is, you want to conduct an experiment with minimum cost, you want to conduct your experiment in such a way because that the basic assumptions of statistics are fulfilled, so that you can use the tools of statistical inference, etc. They can also be satisfied. So there are two aspects. In order to reduce the block size, that is, we are trying to reduce the experimental material to be used, we have two options. One option is to use the incomplete block design, and second aspect is to use the confounding. So whenever we are trying to conduct the factorial experiment, we had also discussed that when you are trying to conduct a full factorial, then you try to create the blocks in which you try to assign all the treatment combinations to every block. For example, in case if you are conducting a 2 square factorial, then there are 4 treatment combinations, and within a block all the 4 treatment combinations are going to be used. This means that every block will have 4 plots, and every plot will be getting 1 treatment combination. And if you want to repeat it further, then for example, if you want to repeat it 5 times, then there will be 5 blocks, and each block will be containing 4 plots, and finally you need 20 plots to conduct the design. Similarly, in case if you are going for 2q factorial experiment, then there are 8 possible treatment combinations. What are those? 1, A, B, C, AB, BC, AC and ABC. So in case if you want to conduct a full factorial experiment, then every block will have 8 possible plots, and every plot will be assigned one treatment combination. And similarly, if you try to repeat it, for example, if you want to obtain, say, 4 replication of the experiment, then there will be 4 blocks, and every block will be containing 8 treatment combinations. So altogether 4 into 8, that is 32 plots are needed to conduct the 2q factorial experiment with 4 replications. Now, there is a situation that we do not have the experimental material which is sufficient to conduct the full factorial experiment. For example, in case if I am conducting 2 square factorial experiment, then suppose I have experimental material which is sufficient only for 4 plots. So now I have 2 options. One option is this: I go for complete factorial and I try to take all the 4 plots in a single block and I try to assign all the treatment combinations in those blocks. But then what will happen? Then we don't have any replication. Second option is this: I try to divide the experimental material into 2 blocks. So I can have 2 blocks and every block will have only 2 plots. So now what will happen? Number of blocks will increase from 1 to 2 and the number of replications will also increase. Right. So now the question is this: in such a situation, every block will have only 2 treatment combinations out of 4 treatment combinations. So the question arises here that you have 1, A, B and AB, 4 treatment combination, but you need to choose only 2 treatment combination which can be assigned in every block. So how to do it? And this is how the concept of confounding comes into picture. Right. So now first let me try to explain you that how the things happen. So now let us try to concentrate on these sheets. Right. So what is confounding? So in case if the number of factors or the level increases, the number of treatment combination increases rapidly. So for example, if you try to see, if I try to take a 2 square factorial experiment, then number of treatment combinations are equal to 4. If I try to here 2q, then this is equal to here 8. And if you want to conduct to the power of 4 factorial experiment, then you have 16 treatment combination. So this means here what? That in case if you try to conduct those experiments, then for example, if I try to take here block 1, then block 2, then in case if you are trying to go for 2 square factorial experiment, then you will have here 1, 2, 3, 4 plots in each of the block, and then you can conduct the complete factorial experiment. And similarly, in case if you want to conduct 2q factorial experiment, then you will have here 8 such plots, and then you will need here 8 plus 8 is equal to 16 plots, and so on. So now my question is this, that since we are observing that as the number of factors are increasing, the number of plots required to conduct the complete factorial experiment, that is increasing quite fast, rapidly. So the experimental material which is needed, that also become more, and hence the cost of the experimentation becomes higher. So my issue is this: now I want to reduce the block size. So as soon as I try to make the block size less, the experimental cost will also become less. So now how to get it done? So now we consider the setup of 2 square factorial experiment. So there are going to be 4 treatment combination. What are those combinations? A, B, AB and 1. Right. So now in case if I want to conduct here the full factorial, then I will need the blocks of size 4. That means every block will have 4 plots. But suppose if we have a situation that we can conduct the experiment using the available raw material, which is sufficient only for 2 treatment combination to be tested. So that means here what? That in case if I try to take here a complete factorial experiment, I need here experimental material for plot number 1, plot number 2, plot number 3, plot number 4. But what experimental material we have which is sufficient only for a block of size plot 2? So now my question is this: out of this 4 treatment combination A, B, AB and 1, which are the 2 treatment combinations out of these 4 which are to be assigned in this plot number 1 and in plot number 2? There can be various combinations. There can be AB, there can be AAB, there can be BAB, there can be A1 and so on. So now the question is this: how to get it done? So what we try to do here is the following. First, you try to recall what we have done in the earlier lectures in the case of factorial experiment. Suppose we conduct this factorial experiment in a randomized block design. Right. So you can recall that we had expressed the main effects A, B, AB and 1 like this here: 1 upon 2, small a minus 1 and small b plus 1. And that was the rule that if there is here A, then the sign which is coming here with this here A, this will be negative and other signs will be positive here like this. And if you try to open it, try to expand it, this will look like this: 1 by 2 AB plus A minus B minus 1. And similarly here B, that will become 1 upon 2 A plus 1 and B minus 1. Why? Because this B will make this sign here to be negative. Okay. And in case if you try to expand it, this will become here 1 upon 2 AB minus A plus B minus 1. And similarly, if you go for the interaction effect AB, this will be 1 upon 2 A minus 1 into B minus 1, which on expanding will become 1 upon 2 AB minus A minus B plus 1. And for the 0, 0 effect 1, this will become 1 upon 2 A plus 1 and B plus 1. Both the signs are going to be positive, and when we try to expand it, this will become here 1 upon 2 AB plus A plus B plus 1. Now, after this, we are assuming that we are going to conduct this experiment in an RBD. What does this mean? That in RBD, there will be 2 types of effect that we have to consider. One is the block effect and another is the treatment effect. So in this case, the model of RBD, which is essentially the two-way analysis of various model, will become Yij is equal to mu plus beta A plus tau j plus epsilon ij, where mu is the general mean effect, beta I is the effect of the ith block, that is ith block effect, and tau j is the jth treatment effect, and epsilon ij is as usual the random error component. So assuming that expected value of epsilon ij is 0, we can write this model as expected value of Yij is equal to mu plus beta I plus tau j, and in our given setup, this I will become 1 and 2. Why? Because there will be only 2 blocks. And tau j, that will become j goes from 1, 2, 3 and 4. Why? 1, 2, 3, 4 means there are 4 treatment effects. What are those effects? They are 1, A, B and AB. So now let us try to assign 2 treatment combination in the blocks out of 1, A, B and AB. Now there can be different choices. So here, without any consideration, we are trying to assign the treatment combination 1 and AB in block 1 and another effect A and B in the block number 2. Well, you can choose any one actually. That is not an issue, and after completing this example I will try to show you that if you try to choose another assignment, what will happen. So now I have got here 2 blocks. So let us assume that this block 1 has block effect beta 1 and this block 2 has the block effect which is denoted by beta 2. And what are your here? Tau 1, tau 2, tau 3, tau 4. These are your here 1, A, B and AB. Okay. Now I try to write down the linear model, that is our two-way ANOVA model for this setup. So now what you can do here, that if you try to write down the model for the effect 1. So this I am going to denote by here y, and in the subscript I am denoting here 1, which is indicating the yij corresponding to the effect 1. So according to our model, that is going to be here mu plus beta plus tau, and now I have to choose what is my here tau and what is here my beta. So mu will remain as mu. For this block effect beta, I have 2 choices, beta 1 and beta 2. So now if you try to look here, that this 1 is occurring in block number 1, which has effect beta 1. So this beta will be beta 1. And what is here tau? Tau here is essentially your here tau 1. So this is the treatment effect. And similarly, if you try to go for this second treatment combination, this YAB, then the expected value of YAB can be written as mu plus the block effect beta, and this AB is occurring in block number 1. So this will become here beta 1, and then I will say here tau. What is here tau? Tau here is AB. That is the treatment effect due to AB. Now, if you observe this, A is occurring in the second block. So for this A, the expected value of this here YA can be written as mu plus, now this beta will become beta 2 because A is occurring in the second block, and then tau will become tau A. And similarly for here B, this B is occurring here in second block. So this will become here mu plus beta 2 plus tau B. Okay. Now, using these observations, using these 4 observations, we have to find out the value of main effect and interaction effects. So now you can recall that A was given as 1 upon 2 AB plus A minus B minus 1. So what are these things? These are the values of the yield or values of the response variable corresponding to this treatment combination. So what is this here AB? AB means when I am trying to give here AB in this particular plot, then whatever is the response from this plot, that is going to be denoted by YAB. So just for the sake of simplicity, we try to ignore this factor here 1 by 2 because for a while. I'm not saying that you are going to remove it, but what I'm trying to say, just for the sake of simplicity in the understanding, we are trying to remove it from here. Now this, how this A is going to be computed? This A is going to be computed from the average yield which is obtained from AB, from the average yield which is obtained from here A, the average yield which is obtained here from B, and the average yield which is obtained from here 1. Yield means essentially the response. So now if I try to write down here A hat, then this will become here YAB plus YA minus YB minus Y1. Right. So essentially that is actually expected value of YAB plus expected value of YA minus expected value of YB minus expected value of Y1. So which I am denoting here by this thing. So now in case if you try to write down these values over here, or if I try to simply write down here A is equal to here expected value of YAB plus expected value of here YA minus expected value of here YB minus expected value of here, say here Y1. Yeah, that also can be done. That is more simple to understand. So now if I try to write down this YAB, YA, YB, Y1 from these 4 equations. So you can see here this YAB is here given by this thing. So I can write down here, this is here mu plus beta 1 plus tau AB plus, okay, this is expected value of YA, this here given by here this mu plus beta 2 plus tau A. So I can write down here mu plus beta 2 plus tau A and minus here expected value of YB. So this becomes here expected YB is given by here mu plus beta 2 plus tau B. And finally expected value of Y1. So this becomes here minus expected value of Y1, which is mu plus beta 1 plus tau 1. Right. So you can see here from these equations, this mu, and mu, they get cancelled out. And what about here beta 1 and beta 2? You can see here this is plus beta 1 and this is here minus beta 1, so they get cancelled out. And similarly here this beta 2 here, this beta 2 plus beta 2, and this is here minus beta 2, they get cancelled out. And what we get here, it is only here tau AB plus tau A minus tau B minus tau 1. Right. So just for the sake of simplicity, I can write down here, it say tau AB minus tau 1 plus tau A minus tau B. Why I have done it? Because I will try to explain you after some time. But if you try to observe here, what I have written here is say tau AB minus tau 1 here. And if you try to look here in this block number here, say here 1. Block number here 1. So you can see here I have simply combined the treatment combinations which are occurring in block number 1. And similarly, if you try to see here, I have written here tau A minus tau B. So these are the two effects A and B which are occurring in block number 2. But what is the implication of this? Because I will try to explain you in a couple of minutes. Now similarly, under the same arrangement, if you try to obtain here the main effect B, so I can just keep it here so that you can see here what are those things. And you can see here that this B will be written as here expected value of YAB minus expected value of here YA plus expected value of here YB minus expected value of here y1. So this I can write down from here. Y AB is your here mu plus beta 1 plus tau AB minus expected value of YA, which is mu plus beta 2 plus tau A plus YB. YB is your mu plus beta 2 plus tau B, and minus here expected value of Y1, which is here mu plus beta 1 plus tau 1. So again you can see here this mu, and mu, they get cancel out. This beta 1, this is here plus beta 1, and this is here minus beta 1, so they get cancel out. And similarly here this here beta 2, which is here plus beta 2, and this is here minus beta 2, and this is here plus beta 2, so they also get cancelled out. So basically I get here tau AB plus tau A, minus tau A plus tau B minus tau 1. Right. So, and then finally I try to find out here for this interaction effect AB, I try to do the same exercise. So this AB is going to be here expected value of YAB minus expected value of YA minus expected value of YB plus expected value of Y1. So now, how you observe what will happen? Something will happen which has not occurred in the case 1 and case 2. So YAB will become here mu plus beta 1 plus tau AB, and this y expected value of YA will become mu plus beta 2 plus tau A. Expected value of YB will become mu plus beta 2 plus tau B, and expected value of 1 will become mu plus beta 1 plus tau 1. Okay. Now you see here what will happen. This mu will get cancelled out. And now what are you getting here? This beta 1 and this here beta 1, they are not getting cancelled out, but this becomes here twice of beta 1 minus beta 2 plus tau AB minus tau A plus tau B, minus tau B plus tau 1. Right. Now you try to observe in the three expressions. What happens here means, if I try to write down here more neatly from these sheets, then I can say here when you are trying to estimate here A, then A was simply tau AB minus tau 1 plus tau A minus tau B. And this here B came out to be tau AB minus tau A plus tau B minus tau 1. You can see here from here. And for here AB, which is happening here twice of beta 1 minus beta 2 plus tau AB minus tau A minus tau B plus tau 1. And yeah, I can write down here this block arrangement also, so that it is available in the same sheet. Okay, now if you try to see what is really happening in these two cases, there is only taus are present. There is no effect of beta 1 or say beta 2. Whereas in the third case, when we are trying to assign here AB, when we are trying to estimate here AB, then this component contains the terms related to taus as well as betas. So now what will happen? Once you have chosen your treatment combinations which are assigned in block number 1 and block number 2 in this way, such that 1 and AB are assigned to one block and A and B are assigned to another block, then in this case, when you are trying to estimate A and B, then these are the functions of only tau 1, tau A, tau B and tau AB. But when you are trying to estimate here AB, this is not only the function of tau A, tau B, tau 1 and tau AB, but it is also the function of beta 1 and beta 2. So when you are trying to estimate this quantity, then the value of AB will reflect two components: the component related to the block effect and the component related to the treatment effects. So that means in this case, when we are trying to estimate AB, then the block effects and treatment effects, both of them are mixed together. And you cannot separate out that what is the contribution of block effect and what is the contribution of treatment effect. For example, if I say, suppose AB comes out to be, suppose here 100. Now you don't know that how much is here the contribution of blocks, beta i's, and what is the contribution of here taus. So in this case, what is happening? That in this block arrangement, you can clearly estimate the main effects A and B, but the interaction effect AB is getting confounded. So I can say here, now in this thing, this AB is getting confounded. What does this mean? You can take the meaning of confounding in a very simple word like as mixed up. So when you are trying to estimate AB, then the block effect and treatment effect, they are mixed together and you cannot separate them out. Now, in order to understand this thing, let me take a simple example. Suppose if I try to mix, say glass balls in some water. Suppose if I try to take here a glass which has some here water, and I try to mix here some glass balls. But if I ask you, can you separate them out? You will say yes. You will just take out the glass balls separately and water separately. So in this case, the glass balls and water are not confounded. So the same thing is happening with A and capital B. That when you are trying to estimate the main effect, they are not getting confounded and you can estimate them clearly. But on the other hand, in case if I give you another example and if I ask you that can you mix say in this water some salt, then the question is this: from the water you cannot separate out the water and some salt over here. Well, you cannot argue on the basis of chemistry that you can evaporate the water and then you can collect the salt, because in that case the water is lost. So in this case you cannot separate out the the effect of salt and water after mixing them. Whereas in this case, you can separate them out. Right. So this is the meaning of confounding. That when I say an effect is confounded, that means this effect cannot be estimated. What does this mean? I will try to explain you in a couple of minutes. But then before I go further, let me try to show you here that in case if I try to take another block arrangement, right, suppose instead of the earlier block arrangement, if I try to take a new block arrangement in which in block number 1 I try to assign 1 and B, and in block number 2 I try to assign here A and AB. Then if you try to do the same exercise, then you will find that in this case A is getting confounded. Rather I will request you that you spend some time and try to do the same exercise just by writing AB and try to see. But that will be the final outcome, that in this case A is getting confounded. So now the bigger question comes over here. Who decides that the effects are to be confounded, and who decides that how the block arrangements have to be made? For example, you have seen that in case if you try to take the block arrangement like this one, then A is getting confounded, and if you try to take the block arrangement which you have taken in the earlier example, then AB was getting confounded. Now let us try to see what is really happening and why this is happening. But before that, we have to understand that what is the meaning of confounding. The meaning of confounding is that the block effects and treatment effects are mixed together. They cannot be separated out, and that's what we say, that the treatment effects are confounded with block effects. So now you have seen that I have taken here two types of block arrangement, and you can also observe that depending on the arrangement of the treatments in different blocks, different factors are getting confounded. For example, in the first case, the interaction effect AB is getting confounded, whereas in the second case, the factor A is getting confounded. So what is the moral of the story? The moral of the story is, it is in your control that the way you assign different treatments to different blocks, then a particular effect will be getting confounded, or the treatment effects will be mixed together with the block differences. Why block differences? Because the factor of beta 1 and beta 2 are coming as beta 1 minus beta 2. So the treatment effect is getting mixed up with the block differences, and that is why the effects are going to be confounded. But a basic fundamental question which comes here, what is really happening? That in the first arrangement the AB is getting confounded, and in the second arrangement factor A is getting confounded. What is the statistical theory behind this thing? So now I will ask you a question. Do you remember that in the beginning of the semester, possibly in the first week or at the most second week, I had asked you, I had given you some concept, and I had written it in the bold face in a capital letter on the blackboard, and I have asked you that you please write this definition, and I will ask you to use this definition towards the end of the semester. So now the time has come. Can you really recall what was that definition? That was related to the estimability of the parameters. We had discussed the concept of estimable function, and we had seen that all the functions are not estimable. A function is said to be estimable only when it is in the form of a linear contrast. And there I had written on the blackboard in capital letters that non-estimable functions are called confounded. So now the question comes, how does this definition fits over here? The definition that we had discussed with the proof and derivation, how does it fits here to the statement that in first arrangement AB is confounded and in the second arrangement the factor A is getting confounded? So let us try to observe the arrangement of the treatments combinations in different blocks along with the definitions of those factors and main effect. So what are we going to do? First we will try to observe what is the definition of AB, capital AB, interaction effect in terms of 1A, B, AB. And we will also observe the definitions of main effects, capital A and capital B. And then we will try to verify from the block arrangements that how those treatment combinations have been assigned to different blocks so that a particular treatment is getting confounded. Right? Joydeep, where is Joydeep today? Has you not come to class today again? So you can see here on this sheet I already have written the two block arrangements which I considered earlier, and I also have written the definitions of AB, A and B. So you may recall that AB was AB plus 1, in which these two factors, they have got a plus sign, and then it was here these two factors, small a and small b, and they are here, and then these two factors, these two treatment combinations were occurring with negative sign. And now in case if you try to observe in the block arrangements here, this is your here block 1 and this is your here block 2. So you can see here that these two treatment combinations which are occurring here with positive signs 1 and AB, they are here. And those two treatment combination, the remaining treatment combination A and B, which were occurring here with minus signs, they have been assigned to block AB. So what you can observe here, that when we are trying to confound here AB, then what is happening? That all the factors with positive sign, they are assigned to block 1, and all those treatment combination with negative sign, they are assigned to block 2. Right, okay. Now let us try to understand what is happening in A. If you try to see here, the definition of A is that AB and here A, they are occurring with positive sign, but AB here you can see and here A, they are in different blocks. And similarly here 1 and here B, which are occurring with negative sign, they are also in different blocks. And you can see here that in this block number 1, in block 1 there are two treatment combination 1 and AB, and in the factor A, this AB and 1, they are occurring like this. One is plus sign and one is, and another is negative sign. So AB is with positive sign and one is with negative sign. And similarly, if you try to see here A and B, A is here with plus sign and B is here with negative sign, and they are occurring in block 2 also here with A with plus sign and B with minus sign. And in case if you try to observe here with here B, then AB and 1, AB has got a plus sign and 1 has got a minus sign, so they are occurring in block number here 1. So one of them has got plus sign and another has got negative sign. And similarly, if you come on the second component B minus A, so B is occurring with plus sign and A is occurring with minus sign, so they have been assigned to block number here 2. Now what do you observe here? Think about it. When I am trying to make the block arrangement, then in A, this AB minus 1, what is this? Is it an elementary contrast? Or in general, is it a contrast? Answer is yes. And similarly, for here another component here A minus B, is this also a contrast? Answer is yes. This is also an elementary contrast. What you can observe here, that the treatment combination which have been assigned to block number 1, they have been assigned in such a way so that they are making a linear contrast within a block. Right. AB minus 1, this is preparing a linear contrast. So this AB and 1, they have been assigned to block number 1. Similarly, A minus B, they are also making a linear contrast. In this case, that's an elementary contrast. They have been assigned to block number 2. Okay. Now you try to observe here in B. The same thing is happening in B also here. This is also a linear contrast, and this is also here a linear contrast. So the two treatment combinations have been chosen in the main effects A and B to be assigned in a block such that they are making an elementary contrast, or in general a contrast within a block. That means all those treatment which have been assigned to block, they are in the form of a, or they are the elements of a linear contrast. Whereas if you now try to observe here in AB, AB here is AB plus 1. Both are here with positive sign and both are occurring here in block number 1. You can see here. Whereas in the second block, you can see here this is A plus B. And A and B both are occurring in block number 2. So in the case of AB, the treatment combination 1, A, B and AB have been assigned to the two blocks, block 1 and block 2, such that within the block they are not making the linear contrast. Okay. Now the same thing you can see here in the second arrangement which we had considered, in which the block 1 had 1 and B and block 2 had A and B. If you try to write down here A, A was here AB minus 1 as written above plus A minus B. So you can see here that all the treatment combination with plus sign, say AB and A, they have been assigned to block 2. You can see here. And 1 and B, which are occurring with the same sign, they have been assigned to block 1. You can see here like this. So that means in this block arrangement, the treatment combinations from the main effect A have been assigned to these two blocks in such a way such that they are not mimicking the linear contrast within the treatment combinations inside the block. And in this case we have observed that in this case A will be getting confounded, whereas B and AB, they will not be confounded. That you can verify. Now in case if you try to look at the same argument from a different point of view, means if you try to see here, if I try to write down here AB, then I will say here AB plus here 1 and minus A plus B. So now I will try to look it in the opposite way. Suppose my objective is this, I want to confound AB. So what I try to do, I try to assign AB and 1 in block number 1, and I try to assign here A and B in block number 2. Say A and here B. And in case if I try to assign all the treatment combination with plus sign in one block and all the treatment combination with minus sign in one block, then the corresponding factor is getting confounded. So why this is happening? Because in this block arrangement, AB is not in the form of a linear contrast. And since this is not a linear contrast, so this is not estimable. And when it is not estimable, this is confounded, because non-estimable linear parametric functions are called confounded. Right? Okay. So now I will try to conclude this lecture. So what we have learned: number one, the effect which we want to confound is in our control. And in order to confound a particular factor or an interaction effect, what we have to do? We have to write the main effect or the interaction effect in the proper format in terms of the treatment combinations, and then I have to collect all the treatment combination with plus sign and all the treatment combination with minus sign. Then all the treatment combinations which are with plus sign, they will be assigned to one block, and all those treatment combinations which will be assigned to another block. So this is how you will confound any particular effect or main effect or interaction effect. So execution of or the determination of the treatment combination to be assigned in a particular block such that a known or a predetermined effect gets confounded, it is pretty simple. But my objective was to explain you that why this is happening. This is because of the simple result that is related to the estimability of the linear parametric function. That a linear parametric function is estimable only when it can be expressed or it can be written in the form of a linear contrast. Possibly you have not thought in that direction, that result is going to be used over here. The second question comes that when I started the lecture, I talked about the decreasing the block size or reducing the block size. How it happened here? So you can see here in this case, when I am trying to consider a 2 square factorial experiment, every block will have 4 treatment combination. Every block will have 4 plots to execute a complete factorial experiment. But when you are trying to confound one effect, then the block size is becoming half. So the block size that was becoming that was 2 square, that is 4, it has now become 2. So instead of having experimental material for 4 plots, we will need the experimental material only for 2 plots. And this is how the block size has become half. Now, if I ask you that how you will execute or extend this thing to a 2q factorial experiment, now it is pretty simple. In the case of 2q factorial experiment, all the main effect and interaction effect, they can be expressed as a function of a treatment combination. 1, A, B, AB, C, AC, BC, ABC. Well, you might be surprised that why I have not used the order 1, A, B, C, AB, BC, AC and ABC. So this I will try to explain you in the next lecture, that why I have used this particular order. But the moral of the story is this, that I will try to write down my main effect and interaction effects as a function of 1, A, B, C, AB, BC, AC and ABC. And then I will try to collect all the treatment combination with the same sign, with plus sign and with minus sign. All the treatment combination with the same sign will be assigned to one block. That is, all the treatment combination with the positive signs, they will be assigned to block number 1, and all the treatment combinations which are occurring with negative sign, they will be assigned to block number 2. And then that effect will become confounded. And the block size will be 2 cube, that is 8 treatment combinations have to be assigned in every block to conduct the complete factorial. Now that becomes half. That is 4 plots. 4 positive signs treatment combination in one block and 4 treatment combinations with the negative sign in, say, another block. So the block size has become half. This gives us a further understanding that when we are trying to confound one effect, then the block size is becoming half. But suppose if I want to reduce it further, then what we have to do? So I will try to show you later on that when you are trying to confound in general an effect, then the block size become half. So if you have 2 factors which are getting confounded, then the block size will become further half, that is 1/4, and so on. So there are some rules by which we can find that when we are trying to confound the factors, what happen, what are the rules to be followed while determining the treatment combinations to be assigned to a blocks when we are trying to confound different types of say effect. All those things I will try to discuss in the next lecture. And next lecture I will try to give you some basic definition, and then I will try to show you some mechanical rules to find out the this confounding effects. So till then, you enjoy, and I will see you in the next lecture. Till then, goodbye.